So now we've learned how to deal with the kind of easy problems that would come along here, but what do we do when we have strong acids and weak acids? What happens if we have mixtures of acids? So we're going to answer some of those things. We're going to be talking about acids in this one and bases in the next one, so just be aware. So finding the pH of a strong acid is really simple. For strong acids, they ionize completely. So all we have to do is they do it only one at a time, so we have to consider the ionization H one at a time, and then we have to move forward from there. And the concentration of the strong acid is exactly the same as the H plus ion concentration. So that's pretty simple. So if we find the pH of 1 molar HCl, well, we know how that works, right? What contributes to H? HCl is a strong acid. So we know that the negative log of 1, and we get the answer of 0. So we have a 0 pH with 1 molar HCl. Okay, so it's pretty simple. We already knew that. Okay, so we want to find the pH of 0.1 molar HNO3. Well, it's the same thing, right? pH equals the negative log of the concentration of the acid. 0.1 molar, okay, and we get 0.1, clear, nope, wrong one, log of, negative log of 0.1, and we get an answer of 1 is the pH. Okay, so pretty simple. Yep, I wrote over top of my stuff. Okay. So, pretty simple stuff. So sometimes an acid is so dilute that water is actually better. So an example, a pH of 1 times 10 to the negative 10th molar HBr. So what do we know? What contributes? HBr contributes. But water could be an acid too. So we see that HBr is 1 times 10 to the 10th molar, and H plus ions, and water is 1 times 10 to the negative 7th molar. So water in this case is actually a better acid because it has a higher concentration of H plus ions than the magnesium bromide or the hydrobromic acid does. So in really dilute situations, we have a situation where water could be greater, so we know it's a pH of 7 because we're always going to take the one that is stronger or the one that shows more acidic character. Okay? So we know that that's the pH of 7 because water is a stronger character there. If we took 1 times 10 to the negative 10th, we get a basic, and that's not what we want. Water is going to contribute there. Okay? So how about weak acids? Well, guess what? They don't ionize completely, so they make an equilibrium. So this, ladies and gentlemen, is where equilibrium starts applying to acids and bases. So we're going to write an equation with water using Bronsted-Lowry definition. They'll have something called a Ka. K is an equilibrium constant no matter what. When it has an A with it, it means the equilibrium constant of a weak acid. That's exactly what that's talking about. So we don't have to panic here. All we have to realize is that we're dealing with equilibrium, the same stuff that we've dealt with for the last week or so, and it's going to be the same. That means ice tables, that means the whole shebang. So the relative strength of acids compared to each other can be found by comparing Ka values. Strong acids have a Ka of infinity. Weak acids have known Ka values, and you can look them up. You can also find Kb of its conjugate base by, well, this is a calculation that you're probably going to need to be familiar with. And again, this is also on your sheet. It tells you exactly what it is. So it tells you that the Kw is equal to Ka times Kb. So if you wanted to find the Kb of the conjugate acid, you would take the Kw divided by the Ka. And then you would find the Kb of the conjugate acid of that thing that you just put into water. Okay? So this is all kind of put together. And again, I will tell you, all of these equations are on the green sheet. So everything that we've talked about in equations is really on the green sheet. The only thing they don't do is they don't tell you what the opposite of log is. But you know the opposite of log. It's on your calculator. It's above the LOG key. It's the times 10 to the x. The X would be the negative pH or the negative POH, depending on what you're calculating, okay? So this is also a really good thing to make sure that you're remembering, because we can calculate other things based upon this, okay? So here we go, an example. Find the pH of 1 molar hydrofluoric acid. So we look up the Ka for our weak acid. Okay, we first set up the ice table. Here's our ice table. So we know the Ka because we've looked it up. It's 7.4 times 10 to the 7th. And then we go back for just a second. So we see the differences, right? So 7.4 times 10 to the negative 7th is our Ka. Okay, so we are going to set it up. So we know that these two things are on top. Water is not included in the equilibrium expression here. That's why it's X'd out. And then we have HF on the bottom. So we've got X squared on the top and 1.0 minus X on the bottom. So that's what we see next. Okay. But this change is very small because I have, excuse me, let me erase something here. I'm sorry, that was 10 to the 4th, not 10 to the 7th. I apologize. Okay, because we have very small, this is going to be a very small change. So what we're going to do is we're going to assume that it stays 1. Okay, so, and all we have to check is to make sure it's within the 5% rule. So what does that mean? And we've been seeing that a couple times through equilibrium. So basically, if we make the assumption that the change in X here is going to be so small that it makes very insignificant difference, what we have to do is we have to check to see if our answer is within 5% of the actual first concentration. So if I take 2.7 times 10 to the negative 7th and second and divide it by 1, then I get my answer. So 2.7 times 10 to the negative 2nd divided by 1, and I get 2.7%. And so it's within 5% of the actual value. So it's okay to do. The lower the exponent, the better that assumption is. That means the lower the error you get. But you can assume it's things that are times 10 to the negative 4th or smaller. Anything else is too great, and you're going to have to solve things a little differently. So there is our concentration, and we're supposed to be, I believe, finding the pH. So what is X? X is the hydrogen ion concentration. So the pH, we take the pH of that number, and we get 1.57. Okay, so you see what we did. We just took this number and we put it right there, and we get the pH of that number. So we used an ice table to calculate this number. We used an ice table to calculate this number, and then we plugged it into the pH calculation. Okay, so find the molarity of acetic acid, and the pH of the solution is 4.15. Now that's pretty important. So here we go. We have an acetic acid solution. We have ice table. We don't know what the concentration is. We know we want to change it by minus X. And we know that we have these for things. So, but we do know this. We know this concentration. How do we know that concentration? Because it's right here. Remember, I can go backwards in my calculation, figure out the concentration. The concentration, remember, is equal to 10 to the negative pH. Okay, so I know that the H plus concentration is 10 to the negative, nope, sorry, I can't use my calculator today, 10 to the negative 4.15. So I know that this concentration is 7.08 times 10 to the negative 5th. I know that concentration. So guess what? Now I can solve from a question mark, because I can look up what acetic acid's Ka value is, okay? So I have a pH of 4.15. So that means that there is the concentration of H plus. Now I can see I've looked up the value for my Ka, and I plug everything in and I solve for the question mark. Okay, so it's just a little math here. So I get 2.8 times 10 to the negative 4th molar. That was the original concentration of the acetic acid. Okay? It's not hard. It's just using equilibrium, okay? So this is just another equilibrium application. I don't want you to be afraid of this. You already know how to do it. You just have to apply it to a new situation and then use the pH calculation to do stuff. So it's the same thing as equilibrium. We're just upping it with pH, okay? That's it. So, give you the initial concentration of unknown acid and find its pH and pKa. So here we go. We have this acid. I'm going on. Okay. We have this acid HQ. We don't know what HQ is, but we know that HQ, when added to water, HQ when added to water, okay, forms H plus Q minus, right? We know that happens, so we set up ice. Okay, so we want the initial concentration. We don't know what the initial concentration is. We know it's going to be minus X because it's a 1 molar solution, so we have question mark minus X here. We don't consider the water, so we don't worry about that. We know these are 0 to begin with, but I'm going to get X and X here, okay? So X and X. Oh, actually, I do know the concentration. I'm sorry, I do know the concentration over here. It's 0.05. I'm sorry, 0.05. I do know the concentration. What I want, I'm looking for the Ka, okay? So I've got that, but I also have the pH, okay? So I also have the pH. So what does the pH tell me? The pH tells me the concentration of H. So the concentration of H, right, is going to be, I did this one already, so it's going to be 4.9 times 10 to the negative 6th, okay? So everybody got that. So I had to change the question marks to 0.05, okay? I may have done my initial calculation wrong. So anyway, so here I am. I'm going to erase this part because I need more room, right? Okay, so you've got this table. Eraser isn't nice sometimes, okay? I have to touch everything. All right, so here we go. So to finish this problem up, then I take 4.9 times 10 to the negative 6 and I square it over 0.05 minus 4.9 times 10 to the negative 6th, right? And that is equal to Ka. So we have to just calculate. So we have 4.9 second function e negative 6 squared, oops. Okay, 4.9 negative 6 squared, okay. That gives me that number, and then I'm going to divide it by 0.05 minus 4.9. I'm doing this calculation again because I did it wrong the first time. So what I get here for my Ka is 4.8 times 10 to the negative 10th. And that is my Ka value. There it is. Okay, so again, it's just an ice table calculation, but we're using the information that we have to be able to solve different things. That's all we're doing. And we're plugging everything into the ice table and then we're pulling it out. H plus is because of the pH, okay? So, mixtures of acids. When you have 2 or more acids mixed together, you have to calculate them in order from the best or strongest to the weakest based on Ka. So you compare the Kas. So if both are strong, basically you find the new molarity. So in this calculation, what we have to do is we have to first find the number of moles of H plus and then turn it back into molarity. So how we do that? Well, we take 0.05 times 1 and we get 0.05 times 1 and we get 0.05, and then we take 0.1 times 3 and we get 0.3, and so we have a total number of moles of 0.35. We divide that by 0.1. Why? Because we had 50 and 100 milliliters, so this is the liters, this is the number of moles, okay? So I get a new molarity of 2.33, okay? That's my new molarity. So pH is the negative log of 2.33 or negative 0.37. That's my answer right there. Okay, so I just find the new molarity of H using the amount of stuff that I have, find the number of moles of H, then add them all together, divide by the total volume to get the new molarity, and then you calculate pH from that. So if they're both strong, that's how you do that. Now, calculate the pH of a solution that contains 1 molar HCN and 5 molar HNO2. Now, these are both weak acids, and it says I also want to calculate the concentration of CN. So I'm definitely going to have to do something here. So the first thing I'm going to do is start with the better acid. The better acid is the nitrous acid. So I figure that out. The nitrous acid, I figure out how much H3O plus I have, or H plus I have. There it is. I just used a nice table, ladies and gentlemen. This was the original concentration. This was how I figured it out. I went up and looked up the Kas in a table of Ka values. Okay, so that's how I got that. Not a big deal. Then I go back and I do the second one, and I see, okay, hang on, the concentration here, remember, I already have 0.45, I add it, so I get it, and I know that the change is 1.48, so I basically calculate it based upon the stronger acid. So usually you're calculating the concentration of the H plus ion, or the pH, based upon the stronger acid, but you always want to do the calculation and get the total concentration. Because this is such a small number compared to this, we clearly use the number from our first calculation, but we needed to do this one because we needed the concentration of CN for our problem. Okay? Ice tables, that's all it is. That's all it is, guys. I know you're sitting here going, oh my God, this is so confusing. It's still ice tables. It's just a new application of ice tables. Don't panic. Okay, polyprotic acids. If you have a polyprotic acid, any of these acids up here that furnish more than one H, we have to consider each H separately, and they all have a different Ka. So there's a Ka1 for the first H, and there's a Ka2 for the second H, and even a Ka3 if you have something like HPO4. So how do you figure that out? So typically, Kas are in order from greatest to least. So the first Ka will be the largest Ka, and the last Ka will be the smaller of the Ka. And they're usually by a factor of 100 times smaller than the original. So the conjugate base of a weak acid is a pretty good base, so it would rather act like a base than an acid in most cases. So we know that because when we have an acid going to a conjugate base, that if we have a weak acid, it's going to be a stronger conjugate base. So that kind of makes sense when we think about it in terms of that conversation. So here we want to find the pH of 0.5 molar H3PO4 and the equilibrium concentration of each conjugate base. So we are trying to find the concentrations of each of these plus the pH overall. So what do? We start with the first one. So we start with the first H. Here we go. Here's our ice table for our first H. You can see here's the concentration of H3 plus, and it's also the concentration of the H2PO4 minus. Okay, so that's where we get that. It's just an ice table problem, young people. Oh, this should be scooted over just a little bit. Sorry about that. Okay, so then we go to the next one. This is Ka2. So you just find the values, and we look up the Ka values. They are all available. All right, and we get that we now have, and see, notice here, the H3O plus concentration has changed because we have some there. So then we add it together, and we add these together, and look at what's happening here. Look at what happens. When we add that total, we still only have this much. So the first round still gave us more acid than anything else gave us, okay? So here is the concentration of HPO4 2 minus. All right? Then we go to the next one. Here we go. Notice, again, we have concentration of H plus already in there, and it's being used to calculate, and we can see what's happening here, going on right here. When we solve for X, we get this number. Look at how small that is. Again, we're still using the original concentration, and usually that's what's going to happen, but you got to do it to check. And you can see what the pH is. The pH is 1.42. So we just do a series of ice table calculations, guys. That's all we're doing. And on the test, they're going to give you all the Kas that you need. You have no ability to look up Ka, so if they don't give it to you, you have no way of knowing what it is. And on the multiple choice test, you can't use the calculator, so they're only going to give you things that are pretty easy to do. Okay? So that's the end of that one. Thank you.